All right, so this video here is going to help supplement your studies for the content that's covered in Module 4, since we won't have any time during class to go over this since y'all be taking your exam. So this week's material deals with confidence intervals. So we're going to learn a little bit about the confidence interval for the sample mean and confidence intervals for the population proportion. So as we know up to this point that we use samples to help estimate populations, and the statistics we compute from those samples will help estimate the parameters from the population. So initially, when we've done things so far, we've computed what we call point estimates. So these are single value estimates for population parameters. So when we've computed the sample mean, X bar, that is an estimate of mu. The problem with it is it's almost surely going to be incorrect when we do our assessment. So what we can do to give ourselves a better estimate of what it is we can create what we call an interval estimate. And so the interval estimate is just a range of values that are plausible for that population parameter that we're trying to estimate when it comes to that. So how do we do this in a statistical way? We create what we call a confidence interval. And so in a confidence interval, what we do is we buffer our prediction by a value called the margin of error. And effectively, the margin of error for us is just a certain number of standard deviations away from that mean. So we'll walk through that process and we'll try and figure out how we get it. So in general, if I want to have a certain level of confidence associated with my estimate, I want to buffer it by a specific amount. So how do we figure out what that amount is? If I have some confidence level C, I'm going to buffer it by what we call a Z star value. And we can find those Z star values using our Z tables such that the area between positive and negative Z is equal to whatever that confidence level I want it to be. So for example, if I wanted to create a 90% confidence interval, then my area in between two Z values needs to be 0.9. That'd be the 90% that we're looking at. If I want to create a 99% confidence interval, then the area between my two Z values needs to be 0.99. And so we can use this concept to help us figure out how much we're going to end up buffering our prediction by. So the first thing we're going to do is we're going to just kind of learn the general concept of how do we figure out what those Z star values are. So here's the process that we go about. So we determine what confidence level we want, C, and we compute it in area, right? Not percentage. So 90% would be 0.9, 95% would be 0.95, so on and so forth. We then take that confidence level and we subtract it from 1. Then after we subtract it from 1, we're going to divide that result by 2. And then we're going to find the corresponding Z value from the Z table, and we'll see how we do this. So let's take a look at an example here. 90% confidence level. So if I want to find the critical Z value for a 90% confidence interval, first thing I'm going to do is I'm going to convert that percentage into a decimal. So that's 0.9. And then I'm going to subtract it from 1. So 1 minus 0.9 is 0.1. Lastly, I divide it by 2. That gives me 0.05. So now I'm going to go to my Z table. And I'm going to try and find on the inside here which value gives me the area under the curve to the left equal to 0.05. So as I'm taking a look here, I see that right here, somewhere in between these two values, gives me that value of 0.05. This is 0.0505. This is 0.04947. This falls pretty closely right in the middle of these two. So what is that Z value here? I've got a negative 1.64, and then I've got a negative 1.65. So it's going to fall right in the middle of these two. And so we're going to end up splitting the difference, and we're going to call it 1.645. That's where we get that critical Z value right there, 1.645. Now, although we looked it up on the table and it was a negative number, that's not that important because we're going to end up doing a plus minus with it. So what's critical for us is just to kind of get the magnitude of that number. So my critical Z value in this case would be 1.645. Now let's take a look at the 85%, right? 0.85, we take 1 minus that value to get 0.15, and then we divide that by 2 to get 0.075. So then we would go to our Z table and say, okay, where in the middle do I see 0.075? And then I see right about here, right? 0.7493. That's pretty close. That's about as close as we're going to get using this table. So that corresponds to negative 1.44. And so that's going to be our best guess for it. So our critical Z value is going to be 1.44. Again, remember, with the plus minus going on, that negative sign's not as important as the number that we get. So we'll walk through one together. We're going to do 95%, and I'll explain in a little bit why we maybe skipped the 92% here. So we say, okay, 95% confidence level. The area between is 0.95. So I'm going to subtract that from 1. That gives me 0.05. Then I'm going to take my 0.05 and I'm going to divide that by 2. That's going to give me 0.025. So now when I go to my table, I want to find the value in the middle that corresponds to 0.025. As I take a look, I see that value is right here, 0.025. That is negative 1.96. So in this case, the critical Z value for this one would be 1.96 as my critical Z value for that. So that's the process we go if we want to find that critical Z value for a specific confidence level. Now, this is going to be important to us because we're going to need to know what this value is in order for us to do the calculations that we need to do. So in general, when we compute confidence intervals, there's a few specific intervals that we tend to use. Every now and then you'll see an 80% confidence interval. That's usually not that standard, but it does happen in practice sometimes. What you see a lot more often in practice are these three right here. 90%, 95%, and 99%. These are usually the standards that are used when computing confidence intervals. And so we just want to be a little bit careful because computing other confidence intervals besides these can be confusing. They can be misleading. And it usually means something's going on when it comes to those things. So in general, you're going to see these values right here when you're doing your confidence intervals. All right, so how do we buffer this, right? How do we find that margin of error E that we want to use to add and subtract? Well, here's how we do it. If we're dealing with a confidence interval for the mean, and we know the population standard deviation, we will end up using this equation right here for E. E is equal to Z critical times the standard error. And the standard error we learned last class was sigma over the square root of n. So effectively what I do is I take my estimate for the sample mean, x bar, and I add and subtract the margin of error, which is Z critical times sigma over the square root of n. So that's how we go about computing a confidence interval. So here's the general process that we go through to construct a confidence interval for the mean. First thing is we want to make sure that we meet some assumptions. First one is that we know what sigma is, or we have a really good estimate for it. We have to have a random sample, of course. And then in order to use the Z distribution, if we recall, we need to know that the population is either normally distributed or my sample size is big enough, n's greater than or equal to 30, that I can assume normality going forward. Next, I need to figure out what that critical z value is, because I'm going to need it in order to do a calculation here. And then I figure out my lower bound and my upper bound by adding and subtracting the margin of error from x bar. Normally, when we write confidence intervals, we write them like this. We use a parentheses. We say, here's the lower end point, here's the upper end point. That's what we get. But your book might want you to write it as lower bound to upper bound. And it'll tell you in the problem kind of how it wants you to enter those things as we go through, and we'll see that maybe in an example or two. The statement we usually use at the end, we have to be a little bit careful with. Here's what the statement says. General statement is we are XX% confident, so whatever our confidence interval is, we are that percent confident that the true value of the population mean falls between lower end point and upper end point when we do this. So that's the general gist of how we run through and compute a confidence interval. So let's see an example here where we can do one here and see what we get. All right, so we're interested in the average recovery time of patients who undergo a specific procedure. We sample 40 people, and we find the average recovery time to be 33.2 days. We have some insider knowledge that the standard deviation sigma for this type of thing is normally 7.5 days. Let's construct a 95% confidence interval for that population mean. Okay, so a couple of things we want to check here. First thing is, we have an idea or we know what sigma is, or we have a very good estimate of it. It's 7.5 days. And my sample size is large enough, it's greater than 40. I can now assume normality, and now I can go forward and construct the confidence interval as discussed. So once we have those things, we need to first figure out what z critical is. Now, the cool thing about critical z values is that they are always the same. If it's a critical z for a 95% confidence interval, that value will always be 1.96. For 90%, it will always be 1.645. So that can help us out that once we know them, we don't have to keep going through that process of finding them. We should know what they are. So since this is a 95% confidence interval, my critical z value is 1.96. And once I know that, I'll be able to compute this margin of error. So we find the margin of error by taking the critical z value, multiplying it by sigma, and dividing it by the square root of our sample size n. So when we plug in the numbers we have, sigma 7.5, n is 40, z critical is 1.96, we see that the margin of error is 2.32. So that's what we're going to buffer our sample mean by. So our sample mean was 33.2 days. And so I was able to buffer this by subtracting 2.32 from it to get a lower bound, adding 2.32 to it to get an upper bound, and then we say we've created our boundaries for the confidence. So our confidence interval in this case would be, based on the way your book likes you to write it, would be 30.88 to 35.52. In general, in practice, you'll probably see it written using parentheses, something like this. Just a matter of preference of how you do it. So there's our confidence interval. Our point estimate was 33.2, and we created a 95% confidence interval to get a more accurate prediction, if you will. Obviously, if we have more values in there, it should be more accurate. Range of plausible values. So then we can finish up by saying we are 95% confident that the true value of the average recovery time for patients undergoing this procedure falls between 30.88 and 35.52 days. So that's how we go about computing a confidence interval. So I'm going to copy this stuff over here, and we're going to walk through an example as we see here. All right, suppose I'm interested in the average weight of cinnamon roll packages from the land of Walton. I purchased 50 packs and find the average weight to be 15.5 ounces. They claim that the standard deviation for their process is 0.5 ounces. We can assume that this is sigma in this case. Let's compute a 90% confidence interval for the average weight of a pack of cinnamon rolls. So what we want to do in this scenario is we want to first validate our assumptions that we know what sigma is, and we can assume normality, or at least have enough data. That way we can invoke the central limit theorem and say that normality is a valid assumption. So in this case, we have that, right? Greater than 30 packs. And so now we can go through this process and compute everything. So this time we're doing a 90% confidence interval. So if I come up, I say, oh yeah, 90% confidence interval, my critical Z value is 1.645. So we're going to change this to 1.645. We need to update the values in here. So we need to put in, oh, sorry, wrong tab. Try that again, 1.645. And we're going to turn this into 0.5. And then my sample size is going to be 50. So now we need to plug this into a calculator to see what we get. So I'm going to do that right now. I don't already have this pre-calculated. And we're going to see that we will buffer this by 0.1163. Now, the homework will probably tell you to round it to a certain part. We don't want to round too much, especially when we get close to boundaries. So I'm just going to round it to 0.116. So now that we found the margin of error, all we have to do is buffer the mean by that value. So I have my lower bound as 15.5 minus 0.116. My upper bound is going to be 15.5 plus 0.116. So then I just have to do those calculations, and I should get 15.384 on the first one. And then on this one, I should get 15.616 on. And so we would write our confidence interval here as 15.384 all the way up to 16.516. And then we would have our upper and lower bounds on those values. So that's the process that we go through as we're doing these things. Okay, so that's a general construct. That's how we execute a confidence interval in practice based on data that we've collected. Now, as we're going through and we're trying to collect information, we may be interested in finding a minimum sample size required to give us a specific margin of error. So in practice, this is really important to us because it helps us determine how much data we think we need to collect to come up with some estimate on the back end. So if we take a look at these previous ones, right? I had a sample size of 40, and it gave me a margin of error of 2.32 days. If I wanted to get this interval tighter and say maybe I wanted to predict it within 1 day, well, then I need to collect more data. Right? On this one, we collected 50, and I was able to estimate it within basically close to 1/10 of an ounce. If I was more interested in maybe saying like, half of an ounce, I wouldn't need as much data. So that's why this planning can become important. How much of a buffer do we want to see on the back end as we're estimating this? So if we know what our margin of error we want it to be, whatever that desire is, we can compute a minimum sample size required to get this value. And so that minimum sample size goes from taking the margin of error equation, solving it for n, and we would get the following. We take that Z critical value, we multiply it by sigma, and we divide it by the margin of error E. Once we get that quantity, we square it. Now, this assumes that we know sigma. If we don't, and we have an estimate for S, and we have a large enough sample size, we can use that as well. Well, let's take a look at a practice. So I want to be able to estimate the average amount of time students at Arizona College study on a weekly basis. Suppose I want to report my results using a 90% confidence interval with a margin error E of plus or minus 0.5. That means that 0.5 is going to be E. How many students do I need to sample to achieve this margin of error? Let's assume that sigma equals 2 hours in this case. So I want to find that. I know that I'm dealing with a 90% confidence level. That's going to help me figure out the Z critical. I know sigma is equal to 2, and I want to be able to estimate this plus or minus half an hour when it comes to that. So plus or minus 0.5. So I plug these things in here. I apologize for the typo. Pretty sure the number's still right on the back end, but we'll double check that. I'm going to take Z critical times sigma over E and square. So I get 1.645 from the 90% confidence level. Sigma is equal to 2. My estimate here is 0.5. And then I get an answer of 43.29 students. I'm going to double check that I didn't make any mistakes there. Just a typo. So we're good here. 43.29 students. Now, when we compute a minimum sample size, we always round up. Always round up to the next number that we get right. If we round down, we're going to fall short of our margin of error when we do this calculation. So we always want to round up. So what this tells me is I need to sample a minimum of 44 students to get me a margin of error of 0.5 hours from a 90% confidence. So that's the minimum sample size that we need, and that's how we go about doing that. All right, so let's take a look at a practice problem here, and we'll walk through the process again. So we've created a business making our own health bars, and we need to report the nutritional facts, and the protein must be reported to within 1 gram of the average amount in each bar. So we sample our bars and we calculate the amount of protein that are in there, and we're going to compute a confidence interval about that mean. That's where that plus or minus comes into play. So if I create a 99% confidence interval, and I assume that sigma is equal to 2.2 grams, what minimum sample size do I need in order to be able to determine what that is within plus or minus 1 gram? Okay, so in this case, I'm dealing with 99% confidence. So I'm going to go back up to my little cheat sheet here and say, oh, if it's 99% confidence, I need 2.576 as my critical Z value. So I'm going to use 2.576 now for that 95% confidence interval. My sigma in this problem is 2.2 grams. And I want that margin of error, E, to be 1 gram as we go about it. So the next thing we're going to do is we're going to plug this into our calculator, and we're going to see what we get. So when I plug this into my calculator, I get 32.117. Now, just like we discussed on the previous one, we always round up to get our bars when it comes to that. So in this case, I need to sample a minimum of 33 bars in order to get a margin of error plus or minus 1 gram of protein. So the question is kind of the application of this. Why is this important to us? Why do we care? Well, in certain scenarios, collecting data is costly, right? On the previous example, the more time I have to take finding students and asking them questions and getting that information, that's just time. And maybe this isn't an overly challenging one. Maybe it's just not that costly. But in the situation where we're creating our own health bars, right, we have to sample our own product, which means we're not able to sell that product. So every single one of those bars that we have to sample represents a loss for us. right? So we don't want to go out and be like, well, let's just sample 200 bars. Well, the problem with that is we just can't sell those 200 bars. So if I say, hey, I need to sample a minimum of 33, well, then I can go down and say, I'm only going to sample 33, see what we get. And if I need a couple more, maybe I can do a couple more, right? But that helps us try and figure out that minimum, and that can help us save money on the back end. So that's how we go about doing minimum sample size calculations for a confidence interval about the mean. So next, we're going to talk about confidence intervals for population proportions. So we haven't talked a lot about proportions so far in this class. So this may be the first time some of you have seen it. The general concept is proportion. We've dealt with it a little bit early on when we were doing like relative frequencies, things like that. We were computing proportions, right? And you've had a couple of problems where you've had to calculate the proportion of data that falls in a certain region. So here's a more general way of how we do this, and then we're going to create confidence intervals about the proportions. So we can estimate the population proportion, p hat, as follows. It is x divided by n. X divided by n. N is the sample size. X is the number of successes that we see, however we define success when we're doing things. So X is basically the number of counters over the total number of trials that we run. So that's how we compute an estimate for the population proportion, p hat. Now, note your book uses a notation where they say if we have p hat, the estimated probability of success, we have q hat, which is the estimated probability of failure. And q hat is just 1 minus p hat, right? If we're not successful, then we fail in the case of these problems that we're taking into account. So just a notation that q is 1 minus p, and p is x over n. So when we're dealing with sampling distributions, we talked about the sampling distribution for the sample mean. The population proportion also has a sampling distribution as well. And so the mean of that sampling distribution of p hat population proportion is whatever our p for the population is, and then the standard deviation is going to be the square root of p times q over n. So just a little bit different here for us as we're going about doing these things going forward. So how do we construct a confidence interval for the population proportion? The concept of confidence intervals does not change very much. Here's the concept, right? Point estimate plus or minus a margin of error. That's it. What changes is whatever that point estimate is, and then how we compute the margin of error. But the end result of the process is the same. We're going to use the point estimate and buffer it by that margin of error. So if we are going to do a confidence interval for the population proportion, there are a couple of things we need to check first. First, we need to determine whether or not p hat can be approximated by a normal distribution. And so in order for us to use the normal distribution that we had there, the following things have to happen. N times p hat must be greater than or equal to 5, and n times q hat must be greater than or equal to 5. What this means in practice is I need to see at least 5 successes and 5 failures in order to use the assumption of normality. If I can do that, then I can use the z distribution, and we can go back and find our margin of error using that critical z value. The critical z values for proportions will be the same as they were for the means. So then we have to compute our margin of error, and our margin of error is computed as z critical times the square root of p hat times q hat divided by n. Once we have the margin of error, we add and subtract that value to p hat, the point estimate, and then we create our confidence interval lower bound to upper bound. And then we make a very similar statement that we did, except for now we're making it about the population proportion and not the sample mean. So that's the general concept of what we're doing. So let's take a look at a practice problem and example. So suppose I'm interested in what my true value of my free throw percentage is today. So I go out and I go take some shots in case we didn't know free throw percentages, the percentage of free throws that I make when I go out and shoot. So I go out shot and I shoot 50 free throws and I make 14 of them. So let's compute a 90% confidence interval for my true free throw percentage. So if I want to compute this, first thing I need to do is I need to come up with my point estimate. So I need to figure out what p hat is, and p hat is x divided by n, where x is the number of successes and n is my sample size. We would define success as me making the free throw in this problem. So my estimate for proportion of makes would be 14 divided by 50. 14 made out of 50 attempted. I made a proportion of 0.28. So that's my estimate for p hat, 0.28. We then need to find q hat. Q hat is 1 minus p hat, or 1 minus 0.28, and that would be 0.72. We then need to check our assumptions that we can use the normal distribution. So I find n times p hat and n times q hat, and make sure they're both greater than or equal to 5. When I find n times p hat, I get 50 times 0.28, which is 14. That's greater than 5. N times q hat is 50 times 0.72, which equals 36. Both of those check out. So now I can use the normal distribution going forward. So next step is to compute my margin of error. I want to construct a 90% confidence interval. So that z critical is going to be 1.645. And then I compute square root of p hat times q hat over n. So 0.28 times 0.72 over 50, square root it, multiply by 1.645, and we get a value of 0.104. That's my margin of error. Then I'm going to take my proportion, and I'm going to add and subtract 0.104. So I get 0.176 as the lower bound, and 0.384 as the upper bound. And so then we could write our confidence interval out going forward. The confidence interval for the proportion would be 0.176 to 0.384. In this case, we're dealing with a percentage. We could convert these to percentages because free throw percentages are always listed as percentages in the name. So 17.6% to 38.4%. And then we could write our statement. We are 90% confident that the true value of my free throw percentage falls between 17.6% and 38.4%. So that's how we go about doing a problem like that. So let's walk through another example on a problem that looks like this to see what we get as we go about doing this. All right, suppose we're interested in the proportion of people who take a new mood-enhancing drug and they reported feeling happier after 2 weeks. We sample 73 individuals who took the new drug and see that 61 of them have reported feeling happier. Let's compute a 95% confidence interval for the proportion of people who are feeling happy. All right, first thing I need to do is estimate my proportion, p hat. That's going to be x over n. The number of people who were happier was 61. I sampled 73 things. And so we go to our calculator, we type in 61 divided by 73, and we get 0.8356. Just to keep things simple, now we'll leave it out. I don't like rounding until I have to. All right, so 0.8356. So then we can compute q hat, 1 minus 0.8356, which would be 0.1644. So now I've got p hat and q hat. Now I need to test whether or not I can use the normal distribution. So I'm going to take n times p hat, 73 times 0.8356, and we should get a number of 61. And then n times q hat will be 73 multiplied by 0.1644, and we should get a value of 12. Both of those are greater than 5, so we're able to use the z distribution going forward. So next I need to compute my margin of error. My critical z value is going to be 1.96 because I'm dealing with a 95% confidence interval. And then I plug in my p hats and my q hats and update that sample size. And then I can go to my calculator to figure out what this value is going to be. So give me just a second here. Calculate that. And we should get a value of 0.085. So my margin of error in this case is 0.085. And now what we're going to do is we're going to take our estimate of p hats, 0.8356, and we are going to add and subtract 0.085 from each one of those numbers. So when we do this, I'm going to use my calculator here. I get 0.7506 as my lower bounds. And then when I do my upper bounds, I'm going to get 0.9206. So now that I've got my bounds, I can say that the confidence interval goes 0.7506 to 0.9206. And we're done. We've computed our 95% confidence interval for happiness. All right. So just like we did with the mean, we can compute sample size estimations, minimum sample size estimates for the proportion confidence interval when we're dealing with those things. Now, a couple of things when it comes to doing these is we have to make some assumptions about things. First thing, our calculation is as follows. P hat times Q hat multiplied by the quantity of Z critical over E, all squared. So this assumes that we have some estimate for P hat going in. And if we don't, that's okay. We can use 0.5 as our estimate for P hat. This is what we call the conservative approach because it guarantees that no matter what that proportion is, we will meet our desired margin of error on that value right there. Problem with that is if we use 0.5, that sample size can become very large and cumbersome. So if we have an idea that we're expecting maybe an 80% success rate or somewhere around there, we can use 0.8 for p hat, and that'll give us a smaller sample size required. But if we don't know, 0.5 is the best, safest case that we can use when it goes forward. So let's take a look at an example. So suppose we've created a new procedure to identify unknown aircraft, and we are trying to assess how often our new procedure works. It is very important for us to get this done with as few trials as possible, as each day of testing costs us nearly $20 million. So what is our minimum sample size required if we want to report our success rate with 90% confidence and a margin of error of 10%? That means that E value will be 0.1. So question is, what should we use as our estimate for P hat? If we use 0.5, and we'll do this both ways so you can see it, that value is going to be big. So we're saying that, hey, we're pretty sure that the radar works pretty well as we're doing these things. Let's use 0.8 instead for our estimate. So if P hat is 0.8, that means that Q hat is going to be 1 minus 0.8, which is equal to 0. So now we can estimate what this is going to be. I get 0.8 times 0.2 multiplied by Z critical divided by E. Z critical, right, 90% confidence, 1.645. I'm going to divide it by my margin of error, 0.1. And then I'm going to square that value right there. So now we can compute our estimated sample size here, plug it into our calculators, see what we get. So when I plug this in, I'm going to get a value of 43.29, which we round up to sample size of 4. So in this case, I would need to run 44. So let's see what happens if we are trying to use the conservative approach to guarantee. Now, we got 44, but that involved us having a success probability of 0.8, right? So if we run this test and we don't have a success probability of 0.8 or better, then that's not going to be enough data. So if we use 0.5, this guarantees that no matter what our success criteria is, that we will meet that value. So if we take a look at this one and we say, okay, what if we use that safe approach and see what we get on that? We end up needing 67.65, which we would round up to 68. So if we have a better estimate, we can refine that. If we don't, we need to come down and we need to end up using a much more conservative estimate, right? And so this would be an additional 24 data points that we need to collect. And it's possible that that could just be an extra week's worth of testing and cost us $100 million. So that's kind of where this minimum sample size thing is coming from. All right, let's do an example problem where we walk through everything we've got. All right, so suppose we're sampling a batch of Sour Patch Kids, and we want to compute the true proportion of red candies in the bag. So we want to predict the proportion with a margin of error of 5%, that means 0.05, and a confidence of 95%. How many candies do I need to sample to achieve this margin of error? So the question becomes, what should we use as our estimate for p hat? Now, a couple things about this, right? In the previous example, every day of testing was a significant cost, right? $20 million. Here, if we're looking at sampling Sour Patch Children, we can go to the store and buy a massive bag, right? And do some calculations on it. And it's not that expensive, right? For 10 bucks, we could probably get a pound or 2 bags, and then we could sample from that bag and see what we get when it comes to that. So it's not overly costly. And so using an estimate of p hat being 0.5 wouldn't be terrible. So let's do that up front. Let's use 0.5 as our value when it comes to that. 95% tells me I have a critical z value of 1.96. My margin of error in this case is 0.05, and then I square that value. So we come plug this into our calculator. We see what we get. We get 384.16 candies, which means we need at the very minimum 385 candies that we need to sample from these bags. 385. Now, that's not a huge deal when it comes to those things because they're fairly cheap for us to do. But what if we wanted to refine this a little bit, right? Maybe we're on a budget. We're just using Halloween candy that we still have. Let's take a look at maybe trying to get a better estimate for what we get in those. So if we buy a regular bag of Sour Patch Kids, they've got like red, they've got green, they've got yellow, and I want to say they probably have orange. They probably have 4 colors of candies, and we might assume that they're evenly distributed. So maybe we expect that roughly a quarter of them, 25%, are red, and then 75% are not. So we can come up with maybe a slightly better approximation for what we expect the values of reds to be, and then we can recompute this confidence interval and see what we get when we do it that way. So if we get this, our minimum sample size is now 288.12, and we would only need 289 candies at a minimum. So as we're going through these things, the importance of understanding what we're dealing with, assumptions that are going on, so on and so forth, can be pretty important to us. As we can see, this is a big difference in the number of candies we need. But most of the time when we're doing minimum sample size calculations, it deals with specific aspects of these things, making sure that we're trying to save money on the back end. So that's why we're going to do this. All right, last thing we're going to do during this video is we are going to talk about the differences between two different populations or groups. So everything we've done so far is kind of one single value that we happen to have and that we're taking a look at, right? We're trying to estimate the mean. Here's what we get. We're trying to estimate the proportion. Here's our confidence interval. Sometimes we might be interested in whether or not two different groups or two different populations have different means when it comes to those. So we can create a confidence interval to take a look at the difference in means between two groups, and it's going to be as follows. The same concept holds for confidence intervals. X bar 1 minus X bar 2, that's group 1, that's group 2. We find the difference of that, and then we buffer it by the margin of error E. So how do we compute that margin of error? It's going to get a little more tricky and complicated because now we have two groups that we're dealing with. So if we can still make the assumption of normality, then our margin of error is this. The critical Z value, which is the same as it's always been, times the square root of the quantity, sigma 1 squared divided by n1, sigma 2 squared divided by n2 added together, and that'll give us our margin of error. Now, you do have one or two homework problems that deal with this type of thing. You're not going to see it on an exam, but it is interesting and it's something useful that we use fairly often when trying to compare two groups. So why do we do this as opposed to just doing each one individually and comparing them? Well, we can, but then we have to make some adjustments on confidence level to find a meaningful difference. This just gets it all done in one fell swoop as we do those things. So what we're interested in when we do a confidence interval for the difference in means is this. Is the value 0 in our interval? If the value of 0 is in our interval, then we can't say these two groups are significantly different from one another. There's no significant difference. But if that value of 0 is not in the interval, well, then those two groups can be considered significantly different on the back end. So that's why we end up doing things like this. So on these notes, I had a thing, hey, we're going to do an example problem on the board or on your homework, something like that. But I think what I'm going to do is I'm going to end this here, and then I'm going to try and create another video where we do some example problems from your homework so you can see how to work a problem kind of across all spectrums of these problems that we have. So I think that's it for this. Hopefully this helps, and best of luck on your exam.